Hi, everyone. Welcome to Chapter P. Chapter P is the first chapter of this college algebra class, and the name of the chapter is Basic Concepts of Algebra. And the chapter is exactly as it sounds. We're going to go over some very basic concepts of the study of algebra that we're going to use for the entire course and in future chapters. One thing I'll note is that this first section of Chapter P, section P1, is quite long. There's a lot to go over here. Real numbers and their properties is a very long section, and that's also kind of indicative of most of the chapter, where most of the chapter is very long itself. So if it's a little off-putting that this first section is over an hour long, it's okay. That's normal. Most sections will not be that long. But this is a good microcosm of how the entire chapter goes. So this video, we're going to go over P1, real numbers and their properties, and you see all the different subsections that we're going to go over. So let's get right into it. So we're going to have some classification here just to start with. We're going to deal with constants for the most part in the class. So constants are any numbers that have very concrete values. For example, 3 or 1/2 or -6, all numbers that we can put on a real number line and visualize what that means. Now, the real number line we're going to go over later on in this section, but 3, 1/2, -6, we have an idea on what those numbers are. And then the whole study of algebra is that we want to introduce these things called variables. And in general, variables are letters that can represent any number. So we want to be able to change the value of a variable. We want to be able to change the value in certain situations. And what we're going to do is use letters to represent being able to change, have a value that can be changed. So some very commonly used letters are X, Y, Z, A, B, C, and you could really use any of the 26 letters of the alphabet to be a variable. However, some letters are a little bit more commonly used for other topics. Like, for example, in chapter 1, we're going to start defining I to be one specific value. So you could use I as a variable, but in general, I is used for other things. But again, we will use X, Y, Z, A, B, C for the most part to represent different values. Four core operations are exactly as you'd expect them to be. Addition that we denote with a plus sign, subtraction we denote with a negative sign, A times B, multiplication. So you can use one of two notations here. You can do A times B with this little dot in the middle, and this is a pretty preferable notation here. It gets the idea across of what we're doing. Or you can also use AB without anything in between them in the case where either both things are variables or both things, or one of the things are variables. So, for example, if we wanted to write 17x, you could write 17 times x, or you could write 17x. The only time that we don't use letters or things right next to each other is when both things are numbers. For example, if we wanted to say 17 times 19, we would have to say 17 times 19, because to write them right next to each other would be 1719, like the number 1719. So it's pretty straightforward. But the thing to get across here is that we are not going to use crosses for to denote multiplication. So, for example, when you're growing up, when you first learn multiplication, the multiplication symbol is an X. You would say AXB. But since we're going to start using x to be a variable, it can get confusing if we allow x to be used as multiplication. So in the entirety of this algebra class and in any algebra class ever, you shouldn't use x to denote multiplication. So please don't do that. Division, exactly as we would expect, A divided by B, where we write A over B. And then one last one that's not really an operation, but something we will talk about as time goes on, is A equals B, which just means these two things are equal. First thing we're going to talk about are sets. So sets are a collection of objects called elements. So the things inside a set is an element. We enclose elements in braces. So this is what a set would look like. This would be an empty set with nothing in it. But if we wanted to write every element in our set, we would write them in between these two braces. Some frequently used sets that we're going to talk about. One of them is the natural numbers, which we denote with a capital N. And the natural numbers are all numbers like 1, 2, 3, 4, 5, what we would typically refer to as counting numbers. The next set that goes up the ladder would be the whole numbers, and the only difference from the whole numbers to the natural numbers is that whole numbers include the element 0. So if you were to start counting from 0 and then 0, 1, 2, 3, 4, 5, and so on, those would be whole numbers. After that, we introduce the integers, and integers are the whole numbers, but where we now allow negative versions of the natural numbers. So again, we go 1, 2, 3, 4, 5, and then we introduce 0, 0, 1, 2, 3, 4, 5. But then in the integers, we start allowing those numbers to be negative, -3, -2, -1, 0, 1, 2, 3, and then forever in both directions. The empty and null set, I said the phrase empty set earlier. Empty set is just a set with nothing in it. Null set, set with nothing in it. We can use this empty set notation here, this little 0 with a line through it. There's a couple different Greek letters that kind of look like this as well, but if you write something like this, this gets the point across that it is an empty set. It's a set that has no elements. Or you could also use this empty set of braces where you just don't write anything between them. They mean the same thing. They both mean a set with nothing in it. The only thing I ask that you don't do is put this empty set symbol into a set of empty braces. Basically, what that would mean is a set of empty sets, and that's kind of beyond the scope of our course in terms of we don't want to broach that topic right now. So either use empty braces or use the empty set symbol. Well, you might notice that in the integers, we have numbers that are -3, -2, -1, 0, 1, 2, 3. But what happens when we want to classify a number like 2.5 or -3/4? Well, all those numbers that are in between the cracks of 1 to 2 and 2 to 3 and so on. Well, we want to introduce a set called the rational numbers. Now, rational numbers we denote with the letter Q, and rational numbers is the set of rational numbers is the set of all numbers that can be written as a ratio or as a fraction. More specifically, numbers that can be written as A over B, specifically where B does not equal 0. So very specifically, any number divided by 0 we say is undefined. So we want to make sure that all of these numbers that we can write as fractions do not allow 0 to be in the denominator. All integers are rational numbers because if we have some number A that is an integer, then we can write A as A divided by 1. Well, if we can write A as A divided by 1, this is the definition of being a rational number. So all integers are rational numbers, and you already start to see this progression. Natural numbers set inside the whole numbers set inside the integers set or sitting inside the rational numbers. And we're going to introduce some more sets that kind of fill the other gaps, so to speak, but we'll do that in just a second. So we have a couple different ways we can denote rational numbers, and aside from writing them as fractions, they can also be terminating decimals. So for example, the number 1 over 2 is 0.5, where this is a decimal place version, but it's a terminating decimal place because it doesn't go on forever. Well, just because it goes on forever doesn't necessarily mean it's not a rational number, because we're also allowed to have non-terminating but repeating decimals. So for example, 1/3, if you were to do long division, 1/3 would be like 0.33333, but instead of writing 0.333 so on and forever, we can just write 0.3 repeating. This little bar at the top of the 3 means the number is repeating. Now, just one thing to note, we like writing 0.3 repeating because 3 is what is repeating. You wouldn't want to write 0.33 repeating because that would be redundant. So this is just supposed to be a nice shorthand way of writing everything you see right here. But again, 1/3 is a rational number, and its equivalent decimal place is a non-terminating but repeating decimal, and that's very important. For example, 26 over 99 would be 0.262626, and we would write that as 0.26 repeating. So you want to write the part that is repeating without needing to put so much under a repeating symbol. Converting fractions to decimals, this is something we're very comfortable with. We don't really need to spend a whole lot of time doing, but this is just long division. However you would have divided in elementary school when you first learned about division is exactly how we would do it here in college algebra. So we don't need to spend time changing 1/3 to 0.33333 just to change it to 0.3 repeating. We don't need to spend time doing 26 divided by 9 is 0.262626 or 0.26 repeating. It's exactly how you've done it in the past. And very rarely are we ever going to need to divide in that way. In chapter 3, we do something similar, but chapter 3 is a long way away. However, if we want to convert decimals to fractions, going backwards, we have to treat it in two separate ways. Notice that we only have one type of fraction. We didn't categorize the fractions themselves. We categorize the decimals. Well, if we have two kinds of decimals, we need two different ways of converting decimals back to fractions. If your decimal is terminating, all we need to do is put that decimal place over 10, 100, 1,000, whatever the however many decimal places we have over that power of 10 and just simplify. So for example, in 0.5, if we wanted to convert 0.5 back to a fraction, we would put 5 over 10. It's one decimal place. We only need one power of 10. So you would do 5 divided by 10 and then simplify 5 over 10. If we had 0.53, well, 0.53 is two decimal places. You would put that over 100. So 53 over 100. Okay, but the interesting part here, the thing we should talk about is non-terminating decimals. How do we convert those to fractions if they never terminate, right? You can't infinitely put something over an infinite power of 10. That would be a lot of work. So we have a very specific method of how we do this. I'm going to cut to the whiteboard so we can do this together, and then we'll go from there. Okay, I believe we are now on the whiteboard. So let's practice putting non-terminating decimals back into fractions. So the first example we'll do is that 0.33333 repeating. Didn't mean to put that there. Ooh. Okay. X equals 0.333 and so on. And we know that 1/3 is equal to 0.3 repeating. Okay, well, how do we convert this back to a back to a fraction if this never terminates? We can't just do that. Okay, so what we're going to do is multiply this x by 10. Okay, well, when we multiply any number by 10, it moves a decimal place over one spot. If we were to multiply by 100, it would move the decimal place over 2 spots, and so on. But let's multiply this x by 10. Well, when we multiply by 10, we then get 3.333 repeating, and these 3's never stop. So even though we only had 3 3's written right here, when we move the decimal place over 1, those 3's still extend infinitely. So we don't really need to worry about running out of 3's for this. So here's what we're going to do. We have that x is 0.333 repeating, and 10x is 3.333 repeating. And what we're going to do is subtract them. So we're going to subtract 0.333 repeating. X equals 0.333 repeating from 10x. And what happens is this. Okay, well, if we have 10x minus x, we have 10 apples and you eat 1 apple. Well, now you only have 9 apples. And when we subtract the decimal places, this is why this method is so useful. Well, we have 3 minus 0, and 3 minus 0 is 3. But notice that everything to the right of the decimal place just goes away. 0.333 is the same as 0.333. Well, when you subtract the exact same thing from itself, that just goes away. So just like that, we've gotten to a point where there's no more decimal place, and that's fantastic. What we would do from here is divide both sides by 9 and divide both of those by 3 to get 1 over 3, exactly like we had before. Now we're breaking some sequence here because we haven't really talked about solving equations, but I think we're familiar enough with the process of solving something like 9x equals 3. So that's not too shabby. But okay, let's do another example like this. For example, like the 0.262626 repeating example. Well, we said 26 over 99 was 0.26 repeating. So how would you be able to do this same thing with something that repeats 2 decimal places? Well, if we multiply this by 10, we know it moves a decimal place over only one spot. So you would get 2.626262 forever. But notice that when we go to subtract, everything to the right of the decimal place is not the same anymore. When we subtract them, they're not identical. Of course, they share decimal places, and as you go on infinitely, they kind of go away. But as it's written, they don't perfectly go away. So this doesn't really work in this way. So what we're going to have to do is this. Well, instead of multiplying by 10, why don't we instead multiply by 100? So take x and multiply it by 100. Well, if we multiply by 100, we move the decimal place over 2 units. So then we would get 26, right? 1, 2 units. Decimal place is here now. So 26, and then everything to the right of the decimal place, oh, looks very similar. Well, we don't want to do anything else with 10x, right? That was kind of the bad sheep. We don't want to deal with that. But notice that we have 100x equals 26.262626. And we can now subtract 0.262626. All right, well, you see everything to the right of the decimal place is the same again. And that leaves us with 100x minus x, that's 99x. 26 minus 0, that's 26. And we divide both sides by 99. And we finally get back to the original. So that's how we convert non-terminating but patterned decimal places back to fractions. Now I'm going to cut back to the presentation. Okay, and I believe we're back to the presentation. So now we continue. Well, if we have a set of numbers that represents numbers that can be written as fractions, well, what about all the numbers that can't be written as fractions? What if we have a decimal place that is non-terminating but also non-patterned, where you just continuously make up new numbers in every decimal spot? Well, we have a set for that called the irrational numbers. If rational numbers are numbers that can be written as fractions, then irrational numbers are numbers that cannot be written as fractions. For example, two popular ones are pi and square root of 2. So, for example, pi is roughly 3.14, but you can extend pi infinitely, 3.14159, and so on. If you look up, the never-ending digits of pi, you'll find computers that continue to find different decimal places, which is pretty interesting. Square root of 2 is roughly 1.41, I believe, but it doesn't stop at 1.41. So again, irrational numbers would be the set of all non-terminating and non-patterned decimals. And I kind of mentioned it before, rational approximation. We're going to do that quite a bit. So, you could use the pi button on your calculator to be accurate as accurate as possible. But in normal everyday talk, we sometimes just like to say pi is roughly 3.14. So in some cases, we like to just use 3.14 if our ending result wouldn't be off by that much. The rational numbers with the irrational numbers, so the set of rational numbers with the set of irrational numbers, the set of all numbers that can be written as fractions and the set of all numbers that cannot be written as fractions, they form R, which is the real numbers. Okay, so we actually have this very interesting level up when it comes to the different sets of real numbers. So I'm going to again go back to the whiteboard to show you this kind of progression. So just give me one moment. Okay, and now we're back to the whiteboard. So we initially started with the natural numbers, which was roughly 1, 2, 3, 4, 5, all the counting numbers. And then we introduced 0, which then gave us the whole numbers. So the natural numbers literally sit inside the whole numbers. If a number is a natural number, then it is also a whole number. They're not exclusive. Okay, well then the next progression was to say that we have the integers and the whole numbers all set in the integers. So if it's a natural number, it's also a whole number. If it's a whole number, it's an integer. So by extension, all natural numbers are also integers. Well, we said all the integers sit in the set the rational numbers. So again, if it's a natural number, it's a whole number. Whole number is an integer. Integer is a rational. Well, by extension, natural numbers and whole numbers are also rational numbers. But then that's where that progression stopped. And then we said we have this set on the outside that we'll denote with a capital I just for the purpose of what we're talking about. So we have this set of rational numbers. We have this set of irrational numbers that are mutually exclusive, but they together make up the real numbers. So both of them together gives us the rational numbers. Sorry, the real numbers, excuse me. The set of both of them give us the real numbers. Now, there is one more progression to this that we don't see until section 1.4, but all the real numbers sit inside an even bigger set called the complex numbers. But we're going to leave that for a little while, and we'll come back to that. But now that we have this progression of sets, we can start to classify them. So when we get back to the presentation, we're going to look at an example. Okay, and I believe we are back to the presentation. Okay, so let's do an example of classifying these numbers. So we have a set A that has the elements -6, -3.4, -9/3, -2/3, 0, 3/4, 7/9, pi, square root of 10, square root of 36, 8.8, 9, and square root of 131. Okay, so we want to classify these numbers into the natural numbers, into the whole numbers, into the rational numbers, and so on. But one thing we should do is see if we can simplify any of these numbers right away. Well, notice that -9/3 we can simplify to -3. Square root of 36, we haven't talked about square roots just yet, but square root of 36 would be 6. So let's make that change first. Let's simplify numbers that we do know. Okay, and now let's start to categorize these numbers into all of those sets that we've talked about. So natural numbers are all the numbers that are like counting numbers, 1, 2, 3, 4, 5, and so on. So let's go through our set A and see which of these numbers look like counting numbers. Okay, well, counting numbers are all positive, right? 1, 2, 3, 4, 5. So that immediately rules out all these negative numbers. 0 isn't a natural number. We didn't introduce 0 until the whole numbers, so 0 is also not a natural number. 3/4 and 7/9 are not counting numbers. Pi, not a counting number. Square root of 10, we couldn't simplify that, so it doesn't look like it's going to be a nice rational number for now. But 6 is a natural number. 8.8, not a counting number. It's close, but not quite. 9 is also a counting number, and square root of 131 is not. So the only natural numbers in our question are 6 and 9. Okay, well, we want to extend this to then do the whole numbers. And we can do the rest of these problems in two ways. One way we can do this is say, okay, well, natural numbers are also whole numbers. So anything that's in this set will also be in this set. And all we need to do is find the new elements that are added to the set. We can do that, or we can just rescan the entire set A to determine which is going to be in the whole numbers. So let's rescan, and you'll see that all we did was basically rewrite the natural numbers and just some added elements. So whole numbers was 0 and the counting numbers. Well, that still doesn't include any negative numbers, but it does include 0. It didn't include fractions just yet. Pi still no, square root of 10 no. 6 and 9 were natural numbers, so they're also going to be whole numbers. 8.8 is still not a counting number, and square root of 131 is also still not a counting number. So the whole numbers are 0 and the two counting numbers from the previous set. So again, I want to stress, if it's a natural number, it's also a whole number. Just because it was in the natural numbers doesn't mean we exclude it in the following sets. It still belongs there. So to an extent, we're going to have sets that grow just a little bit. Okay, well, next up is the integers. And the integers would be the whole numbers, and then including any negative counting numbers, so to speak. Well, let's go through our set and see if there's any negative numbers that would also be like counting numbers, just negative. Well, -6, 6 is a counting number, so -6 is an integer. Negative 3.4, not quite. Negative 3 would be an integer, but negative 2/3 would not. And again, if it's a whole number, it's also an integer. So we don't need to go through all this. We can just say the integers are negative 6, negative 3, and everything we've had in the previous sets. Okay, the next extension would have been the rational numbers. And the rational numbers are any numbers that can be written as fractions. And part of our simplification process is that we already picked out the things that can be written as fractions or simplified those kind of things. So let's go through. Well, negative 6 is an integer. It is a rational number. Negative 3.4, terminating decimal, it is a rational number. Negative 3 was an integer, is a rational number. Negative 2/3, that's a fraction, rational number. 0 was an integer, also a rational number. 3/4 and 7/9, oh, both of these are fractions, the definition of rational numbers. Pi, still no. Square root of 10, still no. 6 was an integer, still a rational number. 8.8, terminating decimal, we can write that as a fraction. 9, integer, still a rational number. And square root of 131, not quite. Okay, well, we stopped the progression at rational numbers and we said, well, we have this weird set that wants to do everything different. We have rational numbers and then we have the set of all numbers that cannot be written as fractions. Well, we just found the set of all things that could be written as fractions. So for the first time, if it's going to be in this set, it's not going to be in irrational numbers. It can't be written as a fraction and also not be able to be written as a fraction. So we want to go through our set, pick out all the numbers that can't be written as fractions. But the easiest way to do this is if we found it in the rational numbers, it's not going to be in the irrational numbers. So we have already left out pi, which we've already discussed being a irrational number. Square root of 10, plug it into your calculator. It's not a pretty number. It's like 3 point something, but it never terminates the decimal places. So square root of 10 is irrational. Square root of 131 is roughly 11 point something, both of which don't terminate. So again, if it was a rational number, it can't be an irrational number and vice versa. Okay, well, then we have the real numbers. And we haven't talked about anything that isn't a real number yet. So one way we can think about this is if we have already talked about it, it has to be a real number. But also just more generally, the real numbers are made up of the rational numbers and the irrational numbers combined. Put those two sets together, it happens to be the same as our original set. So we're just copying and pasting all of the numbers in the original set. Awesome. Okay, that's the entire just first subsection into the first section. So again, P1 very long, we continue. Okay, so let's talk about inequalities. And inequalities are expressions that describe the relationship between any two numbers, more specifically any two real numbers. But again, we haven't talked about anything that's not a real number so far. So of our inequalities, we have this notation that says A is less than B, which means that A is literally less than B, right? For example, 2 is less than 3. So we would use this notation to say that this number is smaller than this number or to the left of this number, right? This inequality points to the left. A is to the left of B. Well, numbers to the left of 0 or numbers that are less than 0, we say are negative. And similarly, we have A is greater than B. All the numbers to the right of B, right? This arrow points to the right. All the numbers to the right of B, or we say A is greater than B. 3 is greater than 2. All the numbers to the right of 0, all the numbers that are A is greater than 0, we say are positive. And we also have notation that says A is less than or equal to B, and A is greater than or equal to B. So for example, 2 is strictly less than 3, but 2 is also less than or equal to 3. We know that 2 does not equal 3, but it does still fit this mold of less than or equal to 3. Now, 3 is not less than 3, but 3 is less than or equal to 3. So that's the only added thing. We allow that specific value to now be included. And same thing here. 4 is greater than or equal to 3, but 4 is also greater than or equal to 4. We also have some notation that says some number sits between A and B. We're going to use this in just a few moments as well. If we have a number that is both less than or equal to another number and greater than or equal to another number, well, the only way a number can be less than and greater than another number is if those two numbers are equal. So if this was just a strictly less than or strictly greater than symbol, this couldn't work. There's no number that is less than and greater than another number, but the only numbers that are less than or equal to or greater than or equal to are numbers that are equal to each other. If A is greater than or equal to 0, well, numbers that are greater than 0 are positive, but 0 is neither negative nor positive. And by introducing the greater than or equal to part, we're saying that this number can now be 0. Well, again, 0 isn't positive or negative, so what we can say is A is non-negative. We know it's positive if it's bigger than 0. We know it's 0 if it's equal to 0. So the way we encapsulate both of those in one word is to say A is non-negative. It's not negative. It's everything but negative. Likewise, if A is less than or equal to 0, we say A is non-positive. The trichotomy property says that all pairs of numbers must fit into one of three options. All pairs of numbers must be less than each other, equal to each other, or greater than each other. So, for example, 2 and 3, well, the only way that 2 and 3 are related is when 2 is less than 3. 5 and 25, the only way that they can be written is that 25 is bigger than 5. And the only way that 6 and 6 can be related is if 6 equals 6. So all pairs of numbers must fit into one of these three categories. Transitive property says that if we have a number that is less than B and that B is less than C, well, then by extension, A is less than C. So if 2 is less than 3 and 3 is less than 4, then 2 has to be less than 4. So that's where that comes from. Okay, so I mentioned we'll talk about the real number line later on, and we have finally gotten to that point. So let's jump back to the whiteboard again to go over what some of these things would look like on a number line. Okay, so now we're back to the whiteboard. Let's start by just writing what the real number line looks like. Well, the real number line, believe it or not, is a line. We've got arrows at both ends to say the right end goes all the way to infinity and the left end goes all the way to negative infinity. And usually as a good placeholder, we like to put 0 right there. So all of these numbers to the right of 0 are positive. A is less than 0 if A is greater than 0 if A is to the right of 0. And all the numbers to the left of 0 are negative. So we can say B is less than 0 because B is to the left of 0. Now, to go over some of the other properties that we just talked about, we could say that A is greater than B in this case, or we can say B is less than A. They would say the same thing. If you kind of notice, if we were to reverse A is greater than B, we would get B is less than A. And we can also say that A is greater than or equal to B if we chose a B that is here, 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 anywhere to the left of B, so long as A is bigger than it. But also, A and B can be the same thing since we allow it to be equal to. And same thing for A is less than or equal to B, just everything to the right. So I'm going to erase this just very quickly just to talk about some of the other ones. Some of the other things we talked about is we said the transitive property, And one more property to talk about, we'll talk about the transitive property. Transitive property said that if A is right here, and B is right here, and C is right here, transitive property said if A is less than B, and B is less than C, if A is to the left of B, which it is, and B is to the left of C, then A has to be less than C. And that makes sense because A is to the left of C. Okay, so those are all the inequality properties, or most of the inequality properties we just talked about, but just gives you an idea how we put these things on a number line. Just to give you another very brief example as to what we might want to do. For example, if we put -3 right here, and we put 4 right here, well, then -3 is less than 4. Or we could put 2 here and say 2 is less than 4. We could put 6 here and say 6 is greater than 4, all stuff like that. Alrighty, so let's cut back to the presentation yet again. Okay, and now we're back to the presentation. I think we only need to go back to the whiteboard one more time in this section. But let's go back to talking about sets now that we've talked about some inequalities. You'll notice that when we were writing sets like we had before, that set A from like -6 to square root of 131, those numbers were quite disjoint. They weren't necessarily rhyme or reason, but what if we wanted to have a set of a lot of numbers? How could we write a lot of numbers in a very shorthanded way? So let's build our way up to that. First way we can write sets is the roster method. So the roster method just says lists everything in the set. So for example, we have the set 1, 2, 3, 4, 5. That makes sense. We wrote all the numbers in the set, but we can also, just looking at another example, imagine if we wrote everybody's name in the class in a set. Well, that's why we call it a roster, right? But also, you can already imagine that it would be very tedious to write everyone in the class's name. For classes that are very large, this could take a lot of time. Well, set builder notation, what we can do is introduce this shorter way of kind of generating everything in the set. So maybe rewriting 1, 2, 3, 4, 5 over and over again isn't so bad. But the second that it's like 1 through 100, well, it would take a lot of time for us to write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 100, right? I can't even say it. Like it would take a long time for me to even just say it, let alone write it. So set builder notation would be something that looks like this. What this says is the set of X such that X is between 1 and 5, and X is a natural number, and then end set. So all the numbers between 1 and 5 such that all of those numbers are natural numbers. Well, imagine this set was from 1 to 100. What we could say is 1 is less than or equal to X, less than or equal to 100. And that would take significantly less time than writing 1 to 100 over and over and over again. If we were to extend the idea into what this class is, what you could say is a student, such that the student is in Max-ematics class. Okay, so let's write the set 2, 3, 4, 5, 6, 7, 8, 9 in set builder notation. Well, let's use this as a guide. What we would write is X such that 2 is less than or equal to X, less than or equal to 9, and that X is a natural number. So yes, there's a lot more numbers that are included between 2 and 9, like for example, 2.5 or 7.33. Those numbers are also in between 2 and 9, but we're adding the restriction that X is a natural number. Okay, let's write the set -3, -1, 1, 3, 5, 7 in set builder notation. Well, we got to be a little careful here because we notice that all of these numbers are in between -3 and 7, but they're not all of the numbers in between -3 and 7. Well, here we had all natural numbers, but now we have negative numbers. So all of these numbers are going to be integers. That's number one. But also notice that all of these numbers are odd numbers. You don't see 2, 4, 6, -2, 0. So what we could write is X such that X is between -3 and 7, and X is odd, and X is an integer. So that's one way of writing. That's another way of writing set builder notation. We just add restrictions as we need. If we wanted to write 17, 18, 19, and so on in set builder notation, we could use another inequality that says X such that X is greater than or equal to 7, and x is a natural number. Sorry, 17. 7, not 7, 17. We can write x such that x is greater than or equal to 17, and x is a natural number. You could also technically say that x is an integer because all of these numbers are also integers, but I think it's easier that we just stick to the sets that we know. Okay. Well, now that we know some sets, we can extend this into what we call unions and intersections. Well, the union of any set is written as A union B with this little cup, this kind of U symbol here, right? U for union, that makes a lot of sense. And what A union B says, it's the set that everything sets A and B have together. So you take A, you take B, and you put them together. Okay, well, then we have intersection. So A intersection B, denoted with this, upside down cup, upside down U. This would be everything that sets A and B have in common. So that's actually kind of interesting. This isn't what they have together. It's strictly what they share. Okay. In general, when we're writing unions, intersections, or even just sets in general, we don't like repeating numbers. If we can avoid repeating numbers that are not distinct from each other, that would be ideal. For example, if 2 appears in one set and 2 appears in another set, well, 2 is not distinct from any other 2. But if we were writing like names, they would be distinct because, one person named Max has a different last name from another person named Max who has a different last name. So we would want to repeat in that case, but non-distinct things we don't like to repeat. Numbers in a lot of cases are non-distinct. We also like to write numbers in order. So if you have the option to write numbers in order, you absolutely should. So let's say we have A is everything between 1 and 10. B is everything between 1 and 9. Sorry, all the odd numbers between 1 and 19. And C is all the even numbers between 12 and 20. So let's find a couple different things. Let's first find A union B. Now, A union B says everything A and B have together. So take A, take B, and put them together. Again, restriction 1, don't repeat numbers. So we don't need to write 1 twice. We don't need to write 3 twice. We don't need to write 5 twice, and so on. And we want to write all these numbers in numerical order. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These 5 repeat, but then 11, 13, 15, 17, 19. This would be the most proper way to write this union. A intersection B is everything that sets A and B have in common. So look at A, look at B, and see what numbers they both have. Okay, A intersection B, they both have a 1, they both have a 3, they both have a 5, they both have a 7, and they both have a 9. But they don't repeat anything else. So A intersection B would be 1, 3, 5, 7, 9. B union C says everything that B and C have together. So take B, take C, put them together. But again, don't repeat numbers. Thankfully, nothing repeats in this set, but write these numbers in order. So don't just write 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 12, 14, 16, 18, 20. Write those numbers in order. Last but not least, for unions and intersections, let's do B intersection C. B intersection C says everything B and C have in common, but you might notice that look at B, look at C, and they don't have anything in common. In the event that they do not have anything in common, we can say empty set. You can also use, again, a set of empty braces. Just don't use both notations at once. Use one or the other. And now we want to introduce intervals. So what you might notice that we did in set builder notation is that we had a set like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we would want to write everything or our x such that x is between 1 and 10 and x is a natural number. Well, that's great and dandy, but what about including all of those things in between 1 and 10, like 9.5 or 7.2 and so on? Right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is a very nice set to say. They're just counting numbers. We've been using counting numbers forever, but it's not really encapsulating anything, right? We want to be able to have all the values in between where it's not just 1 and then 2 and then 3. We want to have a nice continuous set of values, and that's where intervals come in. So not only are they going to come in, but they're also going to give us a shorthanded way of even using set builder notation. So roster method can be very long. Set builder notation allows us to sort of put a cap on that, but intervals are going to be really nice for us to write it even shorter. So again, intervals are continuous sets of values, and we have two types of sets, or sorry, two types. We have two types of intervals within that. We have bounded intervals and unbounded intervals. Well, bounded intervals come in also two different types. So we have a whole bunch of different, subtypes of these things. So bounded intervals, the first type we have is the closed interval that we denote A, B in brackets. So bracket A, comma B, bracket. And what this says is everything from A to B, not just the natural numbers, not just the integers, everything from A to B with A and B included. So when we use a bracket, it is including that endpoint. So if we're saying A to B, it's A to B in brackets, that says everything between A and B with A included and with B included. Then we also introduce the open interval, which would be A to B in parentheses. So parentheses A, comma B, parentheses. This says everything from A to B, but not including A and B. So when we use brackets, we do include those endpoints, but when we use parentheses, we don't include those endpoints. So for example, if we had the set 2 to 3 in brackets, that says everything from 2 to 3, including 2 and including 3. But if we have the set 2 to 3 in parentheses, that says everything between 2 and 3 except 2 and 3. So that might include 2.000000001, but not 2. It might include 2.999999999, but not 3. Well, instead of writing 2.000000000 infinitely, 1 in brackets, it's a lot easier to just write 2 in parentheses. Instead of writing 2.999999999 infinitely in brackets, it's easier to just write 3 in parentheses. We also have sets that are neither open nor closed. This happens plenty of times. All it is that one side is open and one side is closed. Nothing wrong with that. It's just that we don't classify it as open or closed. One side's open, one side is closed. In this one side is closed, one side is open. So instead of giving it a name, we just say it's neither, but we're going to be more interested in actually doing things with these intervals instead of naming them. So what this one would say is everything from A to B, A not included, but B included. This would say everything from A to B with A included and B not included. Well, those are all bounded intervals. Then we also have unbounded intervals. Unbounded intervals, as they sound, are any intervals where one bound is infinity or negative infinity. And I'll say bound in quotation marks because technically we can't bound infinity or negative infinity. So for example, this would be like 2 to infinity or negative infinity to 6. This says everything bigger than 2, 2 not included. This says everything less than 6 with 6 included. The real numbers, for example, would be negative infinity to infinity, everything to the left of 0 and everything to the right of 0 and 0 included. So that's how you would write this interval. And infinity in general, we're going to talk more as your time goes on in math. You'll talk more about it in pre-calc. You'll talk more about it in Calc 1. Calc 1 is where you really start to talk about these things. But infinity in general represents a set of increasing values. It's not a value itself. It's representing this value can increase forever. So, for that reason, infinity only uses parentheses. You'll notice that we never put brackets on infinity because we can't include infinity. So if you're using infinity or negative infinity, always use parentheses for that bound, for that endpoint. Okay, well, we can draw intervals on a number line now that we don't have just 1 and 2 and 3. So let's practice writing some of these things on a number line. And I believe this is the last time we need to go to the whiteboard. So let's do it. Okay, so now we're back to the whiteboard, hopefully for the last time. I'm pretty sure it's the last time. But let's say we have our number line, 0 as a placeholder, forever in both directions. And let's start by writing the interval -3 to 4. Well, -3 to 4 would be let's put -3, let's put 4, and -3 to 4 says everything in between -3 and 4. But we need to add one more restriction, and it's the fact that on the open interval -3 to 4, parentheses mean that we're not allowed to be equal to -3, and we're not allowed to be equal to 4. We can be like 3.9999999, but not 4. Well, how we do that is we represent that with an open circle. So we would say open circle -3, everything in between -3 and 4, and open circle for 4. So technically we shouldn't have, oh, I was afraid it was going to do that. So technically we don't want to, have that little inside, go into the open circle. So this would be a little bit more accurate as to what an open interval would look like. Okay, well, let's continue. Let's do some more examples. Okay, the next example is 2 to 6, the closed interval. So same thing, let's take 2, let's take 6, and we want everything in between +2 and 6. But now we need to take into account that we have brackets. And again, the brackets say that we do include those values. So if we have brackets that do include, we like to use closed circles for this. So again, open was using, parentheses was using open circles, and brackets now use closed circles. And this says everything between 2 and 6 with 2 and 6 included. So parentheses use open circles, and brackets use closed circles. Okay, so let's just continue practicing writing some of these intervals. Okay, next up, let's do -3 to 4, but this time 4 closed. So still -3, still 4, still everything in between -3 and 4. But this time, parentheses still used for -3, so we're still going to use an open circle. But this time we have a bracket at 4, so we're going to use a closed circle at 4. Okay, not so shabby. I think this makes a lot of sense. Write all the values in between them, and then just use parentheses or brackets use open circles or closed circles depending on whether or not parentheses or brackets are used. Just to do 2 more examples involving infinity. Let's say we want to do 2 to infinity. Well, 2 to infinity would be 2. We have parentheses, so we want to use an open circle. And then instead of writing like another endpoint, we just take that and extend it infinitely toward infinity. We'll use another arrow there. Don't necessarily have to, but it's good practice to say 2 and then everything to the right of 2. Similarly, if we wanted to do -infinity up to -7, well, let's put -7 here. -7 is using brackets, and then everything in that direction. We'll do one more example, actually. Let's say we have let's do one more example, actually. Let's say we have -2 to infinity, and we'll put brackets. All right, well, -2, closed circle, and everything to the right. There we go. Just to give you some ideas on how infinity would work. Alrighty, so let's go back to the presentation, hopefully for the rest of the time. Okay, well, now that we know how to draw intervals on a number line, let's now practice taking sets that are in set builder notation and write them as intervals, right? We use set builder notation to sort of simplify the roster method, and now we can use intervals to simplify set builder notation. So here we have -5 less than or equal to x less than 5. This says everything between -5 and 5 with -5 included by virtue of the less than or equal to. So we are able to be equal to -5, and that's the same as using brackets. So we're going to use brackets for -5, comma, parentheses for 5. If you don't like the way I jumped to this, you could practice doing these on a number line and jump to the same conclusion that way. So -5 is included, we used a bracket for it, and 5 is not included, so we used a parentheses for it. Okay, we have x such that 0 is less than or equal to x, less than or equal to 10. So this is everything between 0 and 10. But again, 0 is included by virtue of the less than or equal to, and 10 is also included with less than or equal to. So if both of them are included, we're going to use brackets for both. Here, we have everything between 1 and 3, but 1 not included, 3 not included, so this would be 1 comma 3. Last but not least, we have -6 to -5. -6 not included, so we're going to use parentheses for -6, but -5 is included, so -6 comma -5 with brackets. Okay, last but not least, right, I think we may have a few more examples, but x such that x is bigger than 16. What this is saying everything bigger than 16. 16 is not included, so we're going to use parentheses for 16, but this will be 16 to infinity, right? Everything bigger than 16, everything to the right of 16, so 16 not included to infinity. I think this might be the last example, but now everything less than or equal to -1, well, -1 is going to be included, so we're going to use brackets for -1, but notice that this goes forever to the left of -1, everything less than -1. Well, we don't want to write -1 to infinity because we like writing these intervals from left to right. Right? -5 to 5, 0 to 10, 1 to 3, -6 to -5, 16 to infinity. So be careful because this says -infinity up to -1. Everything less than -1, well, that's -infinity, but -infinity is to the left of -1. And again, for infinity, we always use parentheses, but here in this case, -1 is included as a value, so we use brackets. And that brings us to absolute value. Absolute value is a little different from the things we've talked about, but now that we have an idea on what the number line is, we can extend our knowledge to doing these things algebraically. So absolute value in general is the distance from that number to 0. So if you're saying the absolute value of some number, it's asking how far away is this number from 0? Okay, well, if I ask you, how many units away from 0 is 5? You would say it's 5 units away. But also, if I said, how many units away from 0 is -5? You would also say 5 units. Okay, well, 5 is 5 units away from 0. -5 is 5 units away from 0. So in a sense, absolute value is always going to be positive. Okay, well, the notation we're going to use for absolute value is this A and these like long vertical lines. This says absolute value of A. Again, enclosed in this in these long vertical lines. Well, distance is always positive, right? If we're talking about units away, we're usually talking about positive distance. So absolute value of A, kind of like we were just talking about, is always positive. However, don't be fooled because there are ways we can make absolute value negative. If we tack a negative sign on the outside, well, this says take the absolute value of some number and then make it negative. Okay, so we're allowed to do that. So negative absolute value of A would always be negative. Again, absolute value of A is positive, but the second we tack on a negative sign, now the whole thing is negative. So it is possible for us to get negative numbers when it comes to absolute value. Just the absolute value itself is always positive. The absolute value of any number x is defined the following way. It says that the absolute value of x is itself if x is greater than or equal to 0. So if we want the absolute value of 5, the absolute value of 5 is just 5 because 5 is bigger than 0. However, if your number is negative, then we say it's negative x. So negative x. So for example, absolute value of -5 would be -5. -5 is less than 0. So if we plug in -5 into this says -5. Well, double negative cancels out. It's now positive, and that's how we get 5. Uses some properties we're going to talk about at the end of the section, but there we go. We get the idea. So some properties of absolute value. The absolute value of any number is always greater than or equal to 0. So you take any number, you make it positive, it's going to be bigger than 0. However, if you do the absolute value of 0, how far away from 0 is 0? Well, it's only 0 units away. So it can also be equal to 0. The absolute value of a is equal to the absolute value of negative a. So we just saw in the previous slide that if the negative is on the outside, it's negative. But if the negative sign is on the inside, they are then equal. And we'll see examples on the next slide as to why this is true. The absolute value of a times b can be rewritten as the absolute value of a times the absolute value of b. So we're allowed to split up multiplication with absolute values. We can also do the same thing for division, so long as that the denominator is not 0. So the absolute value of a divided by b is the absolute value of a divided by the absolute value of b. The absolute value of a minus b, this is kind of interesting, is equal to the absolute value of b minus a. So here we split up multiplication, here we split up division, but we're not allowed to split up addition and subtraction. The absolute value of a minus b is equal to the absolute value of b minus a. So we can swap them in the case that it is subtraction. Here, how we get that is the following. Absolute value of a minus b, well, we can factor out a -1 from a minus b. And now this is multiplication, so we can say absolute value of -1 times absolute value of b minus a. How many units away from 0 is -1? Well, only 1 unit. And then 1 times anything is just itself. So in total, absolute value of a minus b equals absolute value of b minus a. But yeah, that's right there. Nice. So just to reiterate, we cannot split up subtraction. So absolute value of a minus b is not equal to the absolute value of a minus the absolute value of b. Can't do that. And we also can't say that the absolute value of a minus b is absolute value of a plus absolute value of b. We've been saying that, I don't know why that's highlighted. Okay, these things happen. We're also not allowed to say that this subtraction becomes an addition, right? We like the idea of absolute value making things positive, but it doesn't magically change subtraction signs into addition. So in all these cases, when you're trying to subtract things inside an absolute value, do the subtraction first and then take care of the absolute value. Likewise, absolute value of a plus b does not equal the absolute value of a plus the absolute value of b, so can't do that. Only multiplication and division can be split up, not addition or subtraction. So please, please do not split them up. A is always less than or equal to the absolute value of a. So same thing, every negative number, right? If you take the absolute value of it, it's now positive. Negative is less than positive version. But if that a is positive or it's 0, well, that's going to be equal to itself. Last but not least, we have the distance formula. Distance formula is denoted by d, parentheses, a, comma, b. So again, this is not now an open interval. This is saying distance from a to b, and we denote that as the absolute value of b minus a. However, absolute value of b minus a, we also said is the absolute value of a minus b. So 2 different formulas for distance, but either one is correct. And all this says is absolute value typically says how far away is this number from 0, but the distance formula says, well, how far away is this number from another number that isn't 0? It's only so exciting for me to ask you how far away from 0 is 5. It's a little bit more interesting for me to ask how far away from -3 is 5, or how far away from 13 is 5. And that's where the distance formula comes in. So let's do some examples. Oh, I have no idea why this is stuck on the screen. Hold on. Let's try closing and opening it back up. Okay. That was fixed. Alrighty. So absolute value of 25, just doing some examples. How far away from 0 is 25? Well, 25 units. And how far away from 0 is negative 25? Well, that's also 25 units. So there's a little bit of proof as to why the absolute value of A is equal to the absolute value of negative A. Absolute value of 2 plus 5. Do not split this up. We said on the previous slide we can't split up addition and subtraction. However, what we can do is simplify the inside first. 2 plus 5 is 7. So the absolute value of 7 is 7. Okay? Absolute value of 2 minus 5. Again, do not split up subtraction. We can only split up multiplication and division. So absolute value of 2 minus 5 says take care of 2 minus 5 first. 2 minus 5 is negative 3. Absolute value of negative 3 is 3. Reminder, do not split them up. Absolute value of 4 minus 6. Well, 4 minus 6 is negative 2. Absolute value of negative 2 is 2. And let's do the same thing, but do absolute value of 6 minus 4 instead, just reversing those two numbers. Well, 6 minus 4 is 2, and the absolute value of 2 is 2. So there's proof. Absolute value of B minus A is the same as the absolute value of A minus B. Absolute value of negative 7 times 7. Well, negative 7 times 7 is negative 49, and the absolute value of negative 49 is 49. What we could also have done is say that this is multiplication. We are allowed to split up multiplication, so we can split this up as absolute value of negative 7 times the absolute value of 7. The absolute value of negative 7 is 7. The absolute value of 7 is 7. 7 times 7 is also 49. So some proof as to why we're allowed to split up multiplication. Okay, let's do some division examples. 40 divided by the absolute value of 10. Absolute value of 10 is 10. 40 divided by 10 is 4. Okay. 40 divided by the absolute value of negative 10. Well, the absolute value of negative 10 is 10, and 40 divided by 10 is 4. Okay. 40 divided by negative absolute value of 10. So again, these are very different. That placement of the negative sign makes a very big difference. Here, this says take the absolute value of 10, which is 10, but then make it negative after doing the absolute value. Well, negative 10 is just negative 10. 40 divided by negative 10 is negative 4. So again, it's still possible to get negative answers despite the fact that we're doing a whole bunch of examples with absolute value signs. Okay, negative 40 divided by absolute value of 10. Absolute value of 10 is 10, but negative 40 divided by 10 is negative 4. Negative 40 divided by absolute value of negative 10. Do not try and cancel out these negative signs. This negative sign is stuck inside this absolute value. Well, absolute value of negative 10 is 10, and negative 40 divided by 10 is negative 4. Take care of these things in pieces. By the end of the section, we're going to talk about PEMDAS. And again, there's an order in which we do things. Start small. Don't try and answer the entire question at once. Negative 40 divided by the absolute, negative 40 divided by negative absolute value of 10. Again, negative on the outside says take the absolute value of 10, which is 10, and then make it negative. Negative 40 divided by negative 10 is positive 4. Okay. Let's do some distance examples. The distance from 1 to 6. Well, the distance formula says B minus A in absolute value or A minus B. Let's do B minus A. So the distance from A to B is the absolute value of B minus A. 6 minus 1 is 5. Absolute value of 5 is 5. But also, we can do the same thing, but instead do A minus B. That's totally allowed. 1 minus 6 is negative 5. Absolute value of negative 5 is 5. Okay. Distance from negative 13 to negative 10. Again, absolute value of B minus A. Well, negative 10 minus negative 13. Negative is a positive. negative 10 plus 13, you're $10 in debt, and somebody gives you $13, you now have $3. Absolute value of 3 is 3. But we can also do it backwards. Negative 13 minus negative 10, negative negative creates a plus. You're $13 in debt, and somebody gives you $10. Now you're only $3 in debt, and the absolute value of negative 3 is 3. The distance from negative 15 to 15, well, absolute value of b minus a, negative negative creates a plus. 15 plus 15 is 30. Absolute value of 30 is 30. The distance from 2 to 2, how far away from 2 is 2? Well, 0 units, but here's proof why. Absolute value of b minus a, 2 minus 2 is 0. Absolute value of 0 is 0. Okay. We continue. We got a little bit more to talk about. Again, I know this presentation very long. Not all of them are going to be this long, I promise. So let's talk about some exponents, some PEMDAS, and wrap up. I'll start to wrap up the section with the properties of real numbers, and then we have one more subsection after that. But the section called the real numbers and their properties, we're gonna just kind of summarize all those properties there. Alrighty, exponents. In general, exponents represent multiplication of the same number multiple times. Okay, well, what we write is x times x times x times x so many times. And depending on how many times you do it, let's say that this happens n times, well, this would be x to the n. Okay, so if we have n of these x's, we say it is x to the n. X we say is the base, and n is the exponent. If we say something is squared, what we're saying is x times x. Well, x times x, there's two x's, so that's x to the 2. And again, we like to say x squared as opposed to x to the second power. You're not wrong for saying x to the second power, but x squared rolls off a little bit better. Likewise, for cubed, this would be x times x times x, which is x to the third. And x to the third, a little bit more common than x to the second, but still, we like x cubed a lot. However, after cubed, we just say to the fourth. Well, to the fourth would be x times x times x times x, x to the literal fourth power, and so on. Everything after x cubed is to just whatever power we say it is. X to the 1, any number raised to the 1 power is itself, so x to the 1 is just x. X to the 0, a little complicated. We'll prove it in the next section, but x to the 0 is 1. Unless x equals 0, 0 to the 0 is indeterminate. That's a Calc 1 question for a long time from now. So just for now, we could take it for granted that x to the 0 is 1. Any number raised to the 0 power is 1. Negative x to the n is not the same as negative x to the n. So what you're going to see a lot in this class is that the usage of parentheses is very important. The placement of parentheses is very, very important. So here, when we have negative x in parentheses raised to the n power, this says take negative x and raise it to the n power. But this says take x, raise it to the n power, and then make it negative. So again, placement of parentheses changes entirely what the thing is asking. So negative x to the n, again, is negative x times negative x times negative x so many times. But we can also do this as negative 1 to the n times x to the n. Notice this is like negative 1 to the x times negative 1 to the, negative 1x times negative 1x times negative 1x. So we have n negative 1s multiplied together and n x's together. And we're going to use this property kind of, sort of, but we'll have a nice way of like simplifying how we think about it. Okay, but negative x to the n says take x to the n, do x to the n, and then make it negative. So please, those are very, very different. Do not screw them up. A times b times c divided by x times y times z, all raised to the n, would be all of these things given an n, distributing n, right? We haven't really talked about distribution yet, but we know what that means. So a to the n times b to the n times c to the n divided by x to the n times y to the n times z to the n. However, this is true for multiplication and division. This is not true for addition and subtraction. So if you have things that are added or subtracted inside where we would typically distribute our exponent, we're not allowed to do that. We are allowed to distribute exponents when everything is either multiplied or divided together. We are not allowed to do this when things are added or subtracted. So please be very careful. It's a very common error. You'll probably find yourself making it at least once. So before we actually do some examples, let's just do some very quick setup. Negative 1 to the 1, any number raised to the 1 power, is itself. Negative 1 squared says negative 1 times negative 1, and we know that negative times a negative is a positive. So negative 1 times negative 1 is positive 1. Well, negative 1 cubed would be negative 1 times negative 1 times negative 1. And we know that negative 1 times negative 1, if we group those two together, well, that's just 1, right? Negative 1 times negative 1, we just saw in the previous part that that's equal to 1. So first part is equal to 1, and then 1 times negative 1, any number times 1 is itself. Last but not least, negative 1 to the 4th would be negative 1 times negative 1 times negative 1 times negative 1. Let's group pairs together, and we know each of those pairs, this equals 1 from negative 1 squared. This equals 1 from 1 squared. 1 times 1 is 1. So what you actually start to see is that numbers raised to odd powers, right? This is to the power of 1. This is to the power of 3. And our final answer in each of these lines was negative 1 and negative 1. So negative numbers raised to odd powers are negative, but negative numbers raised to even powers, right? Negative 1 squared gave us positive 1. Negative 1 to the 4th gave us positive 1. So negative numbers raised to odd powers are negative. Negative numbers raised to even powers are positive. Okay, very important. So let's do a whole bunch of examples. 2 to the 7th. 2 to the 7th says 2 times 2 times 2 times 2 times 2 times 2 times 2, 7 times. So 2 times 2 times 2 times 2. I'm already going to forget how many times I said 2. But this, we can plug it into our calculator. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 times 2 is 64. 64 times 2 is 128. But negative 2 to the 7th is negative 2 times negative 2 times negative 2 times negative 2. And you can put all this into your calculator, but let's think about this. This is a negative number raised to an odd power. And we just said on the previous slide that negative numbers raised to odd powers are, in the end, negative. Well, we know what 2 times 2 times 2 times 2 times 2 times 2 times 2 is. I think I said that enough times. That's 128, but since we're taking a negative number, raising it to an odd power, it'll be negative 128. You can also look at it as negative 2 to the 7th is negative 1 to the 7th times 2 to the 7th. So negative 1 to the 7th would be like negative 1. 2 to the 7th is 128, negative 128. But negative 2 to the 7th, no parentheses. This says only raise 2 to the 7th power. This says raise negative 2 to the 7th power. This says just do 2 to the 7th power first. Well, 2 to the 7th power is 128, and the negative sign on the outside, make it negative. Again, placement of negative signs, usage of parentheses is very, very, very important. 2 to the 8th says 2 times 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 2. Well, 2 to the 7th was 128, so 128 times 2 is 256. Negative 2 to the 8th says negative 2 multiplied by itself 8 times. Well, negative number raised to an even power is positive, right? Negative number raised to an odd power is negative. Negative number raised to an even power is positive. So we get positive 256. Or we can also look at it as negative 1 to the 8th times 2 to the 8th. which is negative 1 to the 8th would be positive 1, 2 to the 8th would be 256, so we can get 256 that way. Negative 2 to the 8th, again, no parentheses, says just do 2 to the 8th first. We know that part's 256. Negative, without parentheses, says make the whole thing negative. 2 to the 0, any number raised to the 0 power is 1. Negative 2 to the 0, any number raised to the 0 power is 1. But negative 2 to the 0 says do 2 to the 0 power first and then make it negative. So again, very, very, very important how we write our parentheses. Just to do some more examples, 2 over 7 to the 5th. Again, division and multiplication, we are allowed to distribute those powers, those exponents. So this is 2 to the 5th over 7 to the 5th. 2 to the 5th is 32. 7 to the 5th is 16,807. Negative 2 to the 7th is negative 1 to the 5th times 2 over 7 to the 5th. Well, negative number raised to an odd power is negative. So the whole thing, negative 32 over 16,807. 2 plus 7 to the 5th is not equal to 2 to the 5th plus 7 to the 5th. 2 plus 7 to the 5th is, do the inside first. 2 plus 7 is 9. 9 to the 5th is 59,049. So please, I am begging you, do not distribute exponents across addition or subtraction, only across multiplication and division. Order of operation, PEMDAS, you've talked about this in the past. Please excuse my dear Aunt Sally. I learned it as purple elephants march down Apple Street, and I didn't realize until college that nobody actually said that, but these things happen. PEMDAS just tells us the order in which we evaluate expressions. So the P stands for parentheses, so always do parentheses first. So if you have parentheses in your expression, take care of parentheses first. Exponents, E, after you take care of parentheses, take care of your exponents. Multiplication and division, well, M and D, and this is a common misconception, even though this says P first, E second, this is not M first and then division second. Multiplication and division go in the same step. So you do parentheses and then exponents, but when you go to do multiplication, you do multiplication and division in the same step, in the same line, left to right. Don't take care of multiplication first, all the way through, and then take care of division all the way through. As you go left to right, take care of multiplication and division at the same time. And we can make the same argument for addition and subtraction. Okay, so PEMDAS. One more thing that I'll throw in there is that if you have a fraction, treat the parts of a fraction separately. You'll find a way to accidentally mix it up if you are not careful. So do the numerator first, do the denominator first, and go from there. We're very comfortable with PEMDAS, but let's do a really ugly looking example together. So we have a bunch of parentheses. We got a bunch of division. Let's do this together. So PEMDAS says do parentheses first. So we're going to take care of our expressions in parentheses. And what I'm going to do is do everything in the numerator first, then everything in the denominator second. So let's take care of just the numerator for right now. Well, we have parentheses. We got to take care of this parentheses first. And inside the parentheses, we have a multiplication, and then we have a subtraction. But again, multiplication takes precedence over addition and subtraction. So we'll first do 5 times 2. 5 times 2 is 10. And then just to finish up the parentheses, 10 minus 3 is 7. Well, we have 7 plus 1 times 6. Again, multiplication takes precedent over addition. So 1 times 6 is 6. And then finishing up the numerator, 7 plus 6 is 13. Now let's do the same thing, but in the denominator. Taking care of parentheses, we have addition and we have division, but division takes precedent over addition. I say that right? Division takes precedent over addition. So we do 8 divided by 4 first, and then we can finish up the parentheses with addition. Now, we haven't mentioned it before, but if we have 7 parentheses 3, this says 7 times 3. So This says do the multiplication 7 times 3 first, and then do the division divided by 7, last but not least, plus 1. So the order in which we do these operations is given by PEMDAS. Okay, let's close out this subsection with the properties of real numbers. We've kind of been using them this whole time, and we're not going to spend a whole lot of time like really proving these things. That's for a way later class, but we can talk about them. So the real numbers, the set of real numbers has all these different properties called closure, commutativity, associativity, and so on. Closure under addition says that if you take two real numbers and you add them, you get a real number back. So the real numbers are closed under addition because no matter which two real numbers you add, after you're done adding, you're still within the set of real numbers. And same thing for multiplication. You take two numbers that are real and you multiply them, they're still a real number. So it's closed under multiplication as well. Commutativity, the real numbers are commutative under addition because you could take any two numbers, add them together, but when you switch their order, it's still the same thing, right? 2 plus 3 is the same as 3 plus 2. So the real numbers are closed under addition. Likewise, for multiplication, 2 times 3 is the same as 3 times 2. So the real numbers are closed under multiplication. Associativity, just the ability to move parentheses around. You've seen stuff like this before. The real numbers have identities. They have two types of identities. They have additive identities and multiplicative identities. So the additive identity is 0 because any number plus 0 or 0 plus any number is just itself. So if you want to add or subtract a number to any number to get the same thing back, you would add or subtract 0. So 0 is the additive identity in the real numbers. Multiplication, any number, if you want to get back to itself via multiplication or division, you would use 1. So a times 1 is the same as 1 times a, just a. So 1 is the multiplicative identity. Inverses, similar. The additive inverse to any number is the negative version of itself, or the negated version of itself, I should say. So the additive inverse of 2 would be negative 2, but the additive inverse of negative 5 would be positive 5. And what inverses do additively is that when you add them together, they get back to 0. So a little bit of a connection here between identity and inverses. Same thing for multiplication. Every number in the real numbers has a multiplicative inverse with the exception of 0. If you want to get back to 1, well, 2, you multiply 2 by 1/2, and you multiply 1/5 by 5 to get back to 1. Distributivity, all it says is we can distribute A, so we would do A times B plus A times C. And same thing if we put the C to the right. So distribution, we've kind of been using it before. You know what it means, but there you see it. Okay, some more properties, just talking about them. 0 times any number or any number times 0 is just 0. If you have two numbers or two variables multiplied together and they equal 0, then at least one of them has to be 0, right? If A and B are real numbers, there's no way that two real numbers that aren't equal to 0 multiply to 0. For example, 2 times 3 never equals 0. Negative 5 times 6 never equals 0. The only way that two numbers or two or more numbers can multiply to 0 is if at least one of them is 0, because either A is 0, 0 times B is 0, or B is 0, A times 0 is 0. A minus B, subtraction is technically just addition of negative numbers. So A minus B is the same as A plus negative B. And division, similarly, well, division is just multiplication by fractions. So when you're doing 8 divided by 4, what you're really doing is 8 times 1/4. Now, we know what division means, but yeah, subtraction falls into addition, and division falls into multiplication. And we know that multiplication is just repeated addition. So in some ways, I like to joke in my class saying that subtraction, multiplication, and division don't exist. It's only addition that exists. But, it's just a joke. That's a very oversimplified version of explaining things. And last but not least, we say any number divided by 0 is undefined. In the case where we have 0 over 0, that's indeterminate. That's Calc 1. We're not brushing that here. So properties of opposites and fractions. We've been using some of these already. Negative 1 times a is negative a. Negative, negative cancels each other out. What other ones we got on here? Negative divided by a negative is positive, stuff like that. And these properties of fractions, you see them right here, but I think it's a little bit better if we just do some examples. So let's do that. 128 divided by 24. What we commonly want to do is simplify fractions, right? 128 divided by 24 doesn't really give us a perfect picture of how we can simplify or what it really is, right? 24 is a very big number to divide by. However, what we can do is multiply or divide both numbers by something so that it's a simpler version, right? Not as many numbers, not as big. So what we want to do is find a number that divides both 128 and 24. Well, if you don't right away see a number that divides both, just go for small numbers. For example, 128 and 24, they're both even numbers. So let's divide both by 2. Well, 128 is 2 times 64. 24 is 2 times 12. So what we're saying we can do is that since we were able to rewrite both as a multiple of 2, we can now cancel out those 2's. Okay, so maybe you don't see what 64 and 12 are both divisible by. Well, we can divide both of them by 2 again. And 32 divided by 6, same thing, we can do it one more time. So we just get 16 over 3. But doing it by 2 isn't necessarily the only way to go about doing this. If you see right away that both of them are divisible by 8, go for it. The bigger you can divide by, the better, the less steps it's going to take. So if all else fails, go for 2's, 3's, and so on. But, if you see bigger ones, by all means, go for it. It saves you a lot of time. 1221 divided by 660. Well, they're both not divisible by 2. But let's just say that they're both divisible by 11. So let's rewrite both of them as multiples of 11. Cancel out the 11's. Oh, well, both of these are divisible by 3, and we can do it that way. Again, if you don't see it, go up the ladder. There's no wrong or right way to do it. Fraction multiplication. When we are multiplying fractions, all we're doing is multiplying the numerators across and multiplying the denominators across. So for example, 11 over 20 times 5 over 12. If we are multiplying, all this says is multiply the numerators divided by multiply the denominators. 11 times 5 is 55. 20 times 12 is 240. And we just saw on the previous slide how we can simplify these things. Okay, but you might notice that we could have saved ourselves a little bit of time. When we went to multiply, do you notice that 5 and 20 can be simplified? 5 over 20 would be like 1 over 4. Well, 11 times 1 is 11. 4 times 12 is 48. So this multiplication is 11 over 48. If you don't see stuff like this, that's okay. Go through all the work of dividing both of these by 5 and going the long way like we did on the previous slide. There's nothing wrong with that. All of what we, like something like this is just a tool to save you some time to be a little bit more efficient. But just because you're inefficient doesn't mean you are wrong. So just something to keep in mind. 81 over 7 times 82 over 9. Multiply the numerators, divided by multiply the denominators. And you'll notice that 81 and 9, we can simplify to 9 over 1 and multiply that way. Could have saved us the step. The number 738 is still pretty big. It would have been even bigger if we didn't simplify it right away. Fraction addition and subtraction. So multiplication is really nice because it's just multiply across, but it's not so nice for addition and subtraction. So for fraction addition and subtraction, what we need to do is make sure the denominators are the same. If they are already the same, then you're just adding and subtracting the numerators and keeping the denominators the same. You don't do anything with the denominators in addition subtraction. But if the denominators are not the same, we have to make them the same. Now that's very eerie. Let's do this together. 3 over 5 plus 4 over 5. Well, they have the same denominator, so all we need to do is add the numerators. Add because we are adding these things. If this was subtraction, you would subtract these things. Simple as that. But notice that we kept the denominator 5 the same. Do not also add the denominators. That would be incorrect. Think about it this way. 3 over 5, 3/5 of a cookie, and 4/5 of a cookie. If you have 3/5 of a cookie and 4/5 of a cookie, in total, you have a little bit more than a cookie's worth. But if you were to do 3 plus 4 over 5 plus 5, that's technically less than 1. That would be 7 over 10, and that's not a full cookie. So please, in addition, subtraction, keep the denominators the same. The only time we use both denominators is when we are doing multiplication or division. But in the case of like 3 over 2 plus 4 over 5, notice that 2 and 5 are not the same. So we can't do what we were just doing. We have to make them the same. Well, you've heard of least common denominator, least common multiple. So notice that if 2 and 5 are the same, we could add them. What multiple of 2 and 5 would make these the same? Well, let's multiply the first one by 5. 2 and 5, their least common multiple is 10. Well, how do we get from 2 to 10? By multiplying by 5. But note that we can't just multiply the denominator by 5. If we multiply the denominator by 5, we go from 3 over 2 to 3 over 10. And those numbers are not the same. We change the problem if we don't do that. So instead, what we multiply by is 5 over 5. Because 5 over 5 is just 1. And we know that if we multiply by 1, we don't change anything. Well, likewise, for 4/5, how do we get from 5 to 10? Let's multiply by 2 over 2. So now we just have a pair of fraction multiplications, and multiplication says multiply the numerators, multiply the denominators, and now same denominator, we can add them, and we get 23 over 10. Nice. Subtraction function's just the same, but don't think that you always have to change your both denominators, right? In 2 and 5, they don't share any factors, right? 10 is the first possible multiple for both. But for 12 and 3, notice that 12 is already a multiple of 3. So you don't always need to change both. You can if you want. It would be more inefficient. You would need to simplify later. It doesn't mean it's wrong, just means a little bit more time. So in this case, we only need to change 3. We need to multiply by 4 to get to 12. So let's multiply by 4 over 4. Well, 1/3 times 4 over 4 is 4/12. 13 over 12 minus 4 over 12 is 9 over 12. And that's the same as 3 over 4 after we simplify. So there's that. Fraction division. My screen is so dark. I started recording in the light, and this section is so long that it's already dark. Okay, fraction division. Keep, change, flip to multiplication. So we don't technically fraction divide, so to speak. We only do fraction multiplication. Well, fraction multiplication, what we need to do is this keep, change, flip kind of idea. So let's say we have 7 divided by 4 divided by 1 divided by 3. Keep, change, flip says this. Keep, change, flip says keep the first fraction, change the sign to multiplication, and flip the second one. Keep, change, flip, and now it's just multiplication. So how do we do division? Keep, change, flip gets it to multiplication. 6 over 19 divided by 2 over 57. Keep, change, flip. Notice that 6 over 2 is 3 over 1. 57 over 19, 3 over 1. 3 over 1 times 3 over 1 is 9. 20 over 9 divided by 27 over 25. Well, notice 9 and 27, they have a relationship. 20 and 25, they have a relationship. But all of that canceling out, all that simplification that we do is only when we multiply. So don't try and simplify 27 over 9 and 20 over 25 until we are in multiplication. And now you'll notice 20 and 27 don't work nicely. 25 and 9 don't work nicely. So we just get a nice non-pretty number, and that happens. And last but not least, if we want to evaluate an expression for a given x value, all we need to do is take that x value and plug it in parentheses. And let's see exactly why. So let's say we want to evaluate 2x squared plus 6x minus 1 at x equals 3, and separately at x equals negative 4. When x equals 3, what we do is wherever we see x, write 3 in parentheses. And here's why we need to use parentheses, because if we don't, what you might be encouraged to do would be do 2 times 3 and then square it. But that would be incorrect. Remember that this x, the only thing being raised to the second power is x. So we need to make sure that we do 3 squared first. Even with parentheses, you might be encouraged to do 2 times 3 first. But again, hopefully you see 3 in parentheses squared and you go for doing PEMDAS, right? So 3 squared, take care of that first, and then do 2 times that. If you don't use parentheses here, you're going to think you just wrote 63. That would also be incorrect. So you could write 6 times 3 in this case without parentheses, but let's stay consistent. Let's do the same thing over and over again. Okay, well, 3 squared is 9. 6 times 3 is 18. 2 times 9 is 18. 18 plus 18 minus 1, 35. So again, parentheses, very, very, very helpful. When x is negative 4, even more important that we use parentheses, because if you didn't use parentheses here, you might be encouraged to do 2 minus 4, and that's completely incorrect, right? We have 2 times x in the very beginning. This needs to be 2 times x here. So not 2 minus 4, 2 times negative 4. And again, we want to make sure that that exponent is going to negative 4 entirely in parentheses. If you don't use parentheses, you might be encouraged to do 4 squared and then make it negative, and that would again be incorrect. Here, you don't use parentheses, you're probably just going to subtract. So parentheses, very helpful. They're free, use them. Negative 4 squared is positive 16. 6 times negative 4 is negative 24. 2 times 16 is 32. 32 minus 24 minus 1 is 7. So parentheses, very helpful. And we're going to do a lot more of this plugging in values as the class goes on. So that's finally the end of P1. It's very long. I understand it's a lot of information, but it's the longest section in the entire class. So if stuff didn't stick this time, don't worry about it. Okay, now that I am completely shrouded in darkness, thanks so much for watching, and I will see you in P2.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.